Hi 254. In this section we're going to talk about 11.5 where we discuss lines and curves in space. The idea in this section is really to take what we've done in the xy plane where we've described lines as well as curves, right? Curves can just be thought of as our graphs of functions, things like parabolas and sine and cosine waves and things like that. And we want to be able to generalize them to 3 dimensions. Now there's a little bit of a problem that we're going to run into trying to talk about how to produce these lines or curves in space. And the problem is that in the xy plane there's an understood way that we produce a line. We kind of look at it and we say, okay, we kind of start over on one side and like draw the line in a certain direction, that kind of thing, right? There's like an understood kind of directionality to it. And actually we made that more specific in 253 where you talked about parametrization. We talked about parametrizing curves. And if you remember, what that meant is that we were able to rewrite a path in the xy plane by writing it as each of the variables depending upon another variable, right? There was this parametrizing variable, something like this, right? And then we said something like for t being a real number, right? And if you haven't seen this notation yet, this is advantageous for you to see at this point. This notation over here means t is a real number, right? This little e thing means element of, so t is an element of the real numbers. T is a real number, okay? So this is how we parametrized curves in 2D, right? Okay, in the xy plane, right? That's how we did parametrization, right? And if you remember, that's what this was called from 253. Okay, but now what we want to do is apply that to in 3D to R3, right? And that's exactly what we're going to do here in this section. So the first thing I want to sort of look at is some notation, right? And we can't do exactly what we did in 253, right, where we talked about how to parameterize a curve in 2D, right, in R2. What we want to do now is make use of our notation that we have for vectors, right, to help us with parameterizing these curves and lines in 3 space, right, in R3. So what we do is we say, okay, there is this kind of curve, could be a line, but in this case they're being very general, right? And they have this like curve and it lives in R3. And what we want to do is parameterize it. So we want to be able to say there's a general direction that this path is produced in, right? And imagine a particle or something moving along that path, right? You want to be able to say the particle moves in this direction, right? Okay? It doesn't move this way, right? In general moves this way, right? We're parameterizing it. We're saying that there's an orientation. You did this in 253, I think, by drawing a little arrow, right, on the curve. So you would have seen something like this, and you would have put a little arrow on them like this to denote that there was an orientation to the curve. And we're going to do the same exact thing here, but we're going to do it a little bit differently without maybe the arrows necessarily. You can still put them there to imply the direction, but how we do this is we say that we're going to have what's called a vector valued function, right? And that's this notation right here, this r of t notation. This is really looking a little funky at this point, right? All this is saying is that the x and the y and the z components all depend upon some kind of a parameter. They depend upon a parameter t. And for a certain value of t, let's say t equals 1 or 2 or 3 or 4 or 5 or 5,000 or negative 1,000, right? Because t can be a real number here. For some value of t, that's going to produce a given vector for us, right? So let's say if we said let t equal 1, right? If we let t equal 1, we would have r of 1, right? And what this means is that we would get whatever the x value would be when t is 1, whatever the y value would be when t is 1, and whatever the z value would be when t is 1. Okay, so notice that what this means is that this function, this is a vector valued function, meaning that this is a function, r is a function, because when you plug in a number, it's going to produce a specific vector, right? It's producing a vector, a 3-component vector, okay? And so what that means visually over here in our picture is that for a specific value of t, you lock in a vector, right? Okay, you get a single vector when you plug in a value of t. And as t varies then, the vectors vary, right? And the curve or line, if it was a line straight, would be produced by the little endpoints that are at the ends of these vectors, right? Okay, so, and that's what this means right down here, right? The curve is how the head of that vector moves as t varies, right? And this is going to parameterize the curve for us, okay, in a very interesting way. Okay, now let's see. Here we go. It's not, let me skip the slides. There we go, we'll move on. Let's look at this specifically in terms of a line, right, and sort of break apart this notation a little bit more here, and actually figure out how to describe a line, right, using this idea of a vector-valued function. The way we add vectors is really the basis for the development of the equation of a line in 3D, right, in 3 space. The reason is that when we take a starting vector, for example, something like this right here, yes, this r sub 0, r naught vector right here, this red thing right here. If we add to it a vector v, remember like this, right, where we concatenate the vectors like this, remember that results in this vector here, correct? This blue vector, right? Red plus green makes blue. Not in our class it does, but not in our, right? So we have red plus green is equal to blue, right? Now, what happens if instead of taking 1 copy of v, I were to take 2 copies of v? If I were to take 2 copies of v, I get a different vector. I get a new blue vector like over here, yes? What if I were to take a half a copy of v? Just a half a copy of v, I would get a vector here, yes? And 3/2 of a copy of v, right? I would have 1.5 copies of v. And so you can see that if you vary the number of copies of v that you are adding to this vector right here, this r naught vector, then you're actually going to be producing an entire line right here, yes? Okay? And really what this comes down to is the generation of this equation of a line right here, yes? Which basically says you have some kind of starting point and then you add so many copies of this vector, right? And this looks familiar from what you've done in like algebra where you had y equals mx plus b, right? It's the same kind of an idea, right? It's like you have a starting point, kind of like your y-intercept, right? Like a b kind of thing. And then you say I'm going to add so many copies of some kind of, in this case it's a standard vector v, but before it was like a slope, right? Okay? And so this is basically the 3D generalization of that idea of a line, okay? All right, let's continue on. I think this slide is just showing us an example, so I don't want to necessarily pay attention to that one too much. I really want to get to the point where we actually get to work out some of the notation, right? Because working out the notation for this section is kind of the tricky part. So I think, let me move down to one of the slides where we're working with curves in space. This guy right here. So instead of working with lines specifically, again, we can let it just be a straight up curve. I can't say that right. Yes, let it be a more general curve, right? Where all I have to do is say let each of the components here vary according to what that or independent variable is, that parameter t, right? And before I didn't give any restrictions about t. I just said let it be a real number, right? Which gave us sort of this infinite length curve doing whatever craziness we want it to do, and the craziness will depend upon what each of these components are doing. But if we were to block off that value for t and say it can only be between a and b, then instead of getting this infinitely long curve doing crazy stuff, right, we're just going to get this closed path like this, right? And again, it's going to be parameterized as t varies from a to b, right? And you're going to have vectors r of a, and then these other ones being produced until you finally terminate when t is equal to b. Okay, for our last sort of discussion about sort of definitions and ideas for this section, I wanted to mention the idea of considering what happens to some kind of curve or line in space, maybe as we let t grow, right, as we let t grow infinitely here. And I don't necessarily need that definition, but what I do need is just an example. So let me take an example from our textbook here and just show you how the idea of a limit can be applied to a vector valued function. So let me take an example of a vector valued function from your textbook, and then we will figure out what the limit of that would be, namely what happens to each of the components as the value of t approaches something or goes off to infinity. It can be either one, quite honestly. So I'm kind of looking at number 35 in our textbook in this section, and I'll end the video with this example and I'll let you try to work on some of the lines and curve problems, and then you can ask me some questions. And if there are lots of questions, then I can post some videos with some further examples. And actually, I'm going to write this in the pointed bracket notation instead of using the IJK, simply because it means I have to write less stuff. Negative 2t over t plus 1, and then tan inverse of t. Okay, so what this is really saying here is combining two pieces together from calculus, one of which is saying I have a vector valued function right here. This is r of t, right? Notice that it's a three-component vector. Each of the components depend upon some variable t, right? And then what we're being asked for is what happens to this vector valued function in this limiting process, right? That's what this front thing is saying. Really what it's saying is, what is the vector that this thing tends to approach, right, as t goes to infinity? What's lovely about this is that all we have to do is think about how each of these components behave as t gets large, right? So the result of this limit is going to be another vector, right? Because we're going to be able to say, well, as t approaches infinity, our vector is going to be, our vector valued function's behavior is going to approach a certain vector, right? And we just have to take the limit of each of the components, right? So let's take the limit of each of the components. What's the limit of e to the negative t? Remember, that's exponential decay, and as the exponent gets large, this shrinks away. This next one here is a rational expression where I notice that the degree of the top and the degree of the bottom match, and when that happens I take the ratio of the leading coefficients, so that means I take negative 2 over 1, which is just negative 2. And for this last one, I see that I have tan inverse t, and if you remember anything about the graph of tan inverse t, it looks something like a tangent graph, but flipped around slightly, right? And as t goes to infinity here, that means we're going to be approaching this horizontal asymptote, which happens at pi over 2. So it's going to be pi over 2. Okay? So this right here is the vector that as t goes to infinity, this vector valued function approaches. Okay? For right now, we'll pause because that got us to about 12 minutes for this video. I don't want to make them too long. We'll pause here, and I'll let you sort of digest that a little bit, and then I'll make you another little video with a few more examples in it with equations of lines and working more with these vector valued functions.